Okay, hello. This is our Team 13 project, the Edge Detection Program given for NGR 133. Our group members are Jose Miguel Haro, Emma Block, Hannah Inoegos, and myself, Adrian Prasad. So before we actually begin explaining our code, I thought it'd be helpful to write out what our code is doing in a matrix example. Essentially what we're doing is manipulating the image matrix to get a desired result, which is, in this case, edge detection. So before we can actually begin to talk about the program, I'd like to begin a little bit about speaking about these particular matrices. So every image is essentially a multi-dimensional array, meaning it is a list. So we're presented with an X and Y scale. That's what we see in our face. Those are pixels. But each one of those particular pixels has 3 additional details. And those are going to be the RGB constant values, red, green, and blue. The combination of these things actually gives us our color. For the purpose of our edge detection, this color is not incredibly helpful. In fact, it hinders the process, as we've explained. So we're going to need to grayscale it. Grayscaling is essentially taking that extra 3 bits of multidimensional data and turning them into one piece of data. What we're going to do here, I've drawn out a matrix. Here we have just a matrix of a random assortment. We can assume it's n by n2 or whatever we'd like to call the dimensions. And as you can see, here's the x and y's that we're displayed with. But in the first, there's a red, green, and blue value that corresponds to this particular column, this particular part of the matrix. And we're going to call this one a pixel. So we have a whole bunch of pixels here. To fix this, we're going to want to create a new matrix. In this new matrix, we're instead of having 3 values for each pixel, we're just going to have a singular value. We're going to achieve this by multiplying the red value by a constant, the green value by a constant, blue value by a constant, and then summing them all, taking the sum and putting it to a new matrix that's the same dimension as the last matrix. We're going to be using international standards for this, for grayscaling, which we've explained in our rationale. But this will give you an insight into how the code works. So now we can actually go to Spider and take a mechanical look at the function that we defined for grayscale. So we've first taken in our image, which I will explain later, but we have already taken in our image that is an array with the color data in addition to the X and Y data. So what we're going to do here is first create this empty matrix like we did here. Over here is our new empty matrix. So we take our empty matrix here, and then we're going to search the matrix that we've entered, the original image, the image that we're trying to do our edge detection on. We go here, we search through it, and then we search into the color. We create a loop, and we're going to search every single pixel in this image, every X by Y, and we're going to search all of the color data. We're going to search the red data and multiply by 0.212, the green data, multiply by the constant here, and then the blue data and multiply by the constant here. We sum them, and then essentially we're putting all of these values into the first part of the empty matrix. Then we repeat it for the next pixel, then the next pixel, then the next pixel, until we've completed the row. And then we've completed the column, and then we've completed the entire image, essentially. Then our function calls, we take this new image, our grayscale image, and put it into noise reduction function. So this moves us on to our next part, the noise reduction. What we're essentially doing is using a Gaussian kernel to give us a more average image. To explain this a little bit, we can explain this in a more simple way. Here's our big overall matrix. Let's say it has n1 times n2 dimensions. It's whatever our X and Y is, as I've drawn the X and Y here. We're going to take a little glimpse of each image. So we're going to take a 5 by 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, down. We're going to sum each one of these individually. So add this to this, add this to this, add this to this, add this to this, move row down, add this to this, and then iterate until we've done the whole 5 by 5. Then we're going to divide by 256. Now, after we've done that, we create an X value. And now, if we look over here in the code, we've created another empty matrix with dimensions. So now we're going to take the X, pop it in. Then you may notice that we start from here. So we start our 5 by 5 count from here, 5 here, 5 here. We go to the next pixel, 5 here, 5 here, next pixel. Then we drop down until we take the weighted average of every single one of these. So if we look at the code, here's what it does. We take the blurred image, we create a blurred image, which is the empty row in this case, and we use a 5 by 5 Gaussian kernel. Like I said, the 5 by 5 Gaussian kernel is simply just counting 5 by 5 from a singular point, summing each one of these things, and then dividing by 256, which is exactly what we do here. And we count this for every pixel. We're going to count it for every pixel that we can, because we're essentially counting from the middle. In our code in particular, we start count from here, from the middle of this. But I gave this example here just so you can have an idea that we do iterate through all of the given pixels. So if we look over here, there's actually this really long line of code. Even though it looks very long, it's really simple. It's essentially the counting of the 5 by 5 matrix. So we do this for every pixel, like I said before. And then we get to the end of our function and we take the blurred image, which is all appended onto this blurred image list here, and we call it into our edge detection. So now I can move on to the edge detection part. The edge detection is actually fairly simple and fairly straightforward. So what we're going to do here is we're going to take, just like we did last time where we took a 5 by 5, we're going to take 3 by 3 of this matrix over here, which has now been filled up. This is now our noise reduced image. So what we're going to do here is we're going to take this 3 by 3, we're going to cut it, and we have an X and Y operator. These are our Sobel operators. So in our X operator, it's going to be -1, -2, 0, -1, 0, 0. And the direction and the orientation of the matrix really matters because we're going to essentially need both of these things to create the edge detected image that we'd like. So we have the X image. What we're going to do is actually just multiply each, because we're taking a 3 by 3 and a 3 by 3, we're just going to multiply each character. So we take the -1, and let's just say just for saying sake, we have C1, C2, C3, C4. And these are just elements of the matrix. So we'll take -1 times C1, 0 times C2, 1 times C3. And over here, we can see the results of this. This would give us -C1, 0, C3, -2, C4, 2, C6, and then so on and so forth. Then we would do the same for the Y. So now that would produce essentially the same result, but flipped. Not the same result, of course, but it would be the same mechanical process, essentially, that leads us to this. And we're going to do this on 2 separate counts, creating 2 separate variables, both an X new matrix and a Y new matrix. Now, once we take the X new matrix and the Y new matrix, once we take the new values, sorry, we're going to create a new matrix in the end. We're going to call it the Z matrix. But once we take these X and Y values, we're going to square them both and take the square root, and then we get a Z value. This is our Z matrix. Then we count the Z matrix into each one of these until our row is filled. So now let's actually look over here to see what's going on. So we're creating the X image and the Y image. These are 2 empty NumPy arrays like before. We take in our edged image, and this is actually going to be our final result. So now over here, you can see we have the X operator. It's the same thing as over here. And you can see that we're multiplying by all the constants necessary. So after we do all the constants necessary, we create the matrix, add it up. We do the same thing over here. And then we take the values. So just for clarification, we actually, once we get all these values together, we're going to sum them together. As you see here, we've summed all the values together. This actually does not give us a matrix. This is going to give us a straight scalar number that's going to be put into here. So now that we have all these numbers in, we're going to do, as I said before, square this, square this, add them together and root it and create the z. And then the z is created and added into this empty matrix here. We do this for all the pixels. We search them through, and then we create our new matrix. Now the final part is actually fairly simple. Now, when it comes to edge detection, we care about, is something an edge or is it not an edge? There's no in between in this case. We do not care if it's in between, because you can only be an edge or not an edge, essentially. So we've created a threshold value. If a particular element in a matrix is below this, here, as we can see, this is 0.075, we set it to 0. Now, if it isn't, we set it to 1. The reason we do this is because the edges are going to have a significant value difference from the non-edge values. And this is going to essentially set them in a way that's easily differentiable and having only binary values. This will make more sense once we run the code, if it doesn't already, but this is essentially our way of differentiating the edges and making them out. We determine this threshold value, we determine this threshold value by trying it out and seeing what actually led to the most accurate edges being produced. So finally, we reach our final code, the inputs and errors. So while talking to some of the TAs, we actually figured out that we should be using PNGs and not JPEG images, because JPEG images are actually compressed already. That's going to create a fair amount of distortion in the image. And this is going to make it so the computer is going to have a hard time actually figuring out what the edges are. So we've made it so that if you put in an input and it's not a PNG, the program does not run. And it'll give an error check. So we create a while loop, and this while loop is essentially going to keep going and going and going until you input what it needs. So if you keep putting in errors, it's going to just run you back through the loop. And once you run it, it runs. So if you look over here, I'll just show you what this while loop looks like. So we start when 1 is equal to 1. We choose an obviously true statement to keep the while loop running. Now, we take enter the input, and it'll tell you input a PNG only file. We take a here and we check it. And if the end of your attachment or your file is a PNG, we take it, we do original image, we read it in, and this is how we read in the image to create the matrix. We create pixel height, and the pixel height is actually, as we've seen over here, like I said before, we created these empty matrices with pixel height times pixel width, X and Y dimensions. This reads in the shape, the size of the X and Y dimensions. So the pixel height, because we're looking at the X and Y dimensions are 2 parts of the multi-dimensional array. Then we go over here, program. What this does is it starts the chain reaction of functions. We decided to modularize the code because functions make the code look a lot cleaner, and it's a lot more easy to troubleshoot issues that actually occur. So it starts a loop. This loop starts the program. This function feeds into this function. This function feeds into the next function. Function feeds into the next function until you're finished. Then after that's finished, before the image can actually present to the screen, we want to do a little bit of cleaning up. So when you use matplotlib, which is what we're using to represent our images, you're going to find that you have X and Y ticks, which are your X and Y axes. And this is usually useful if you're looking at a graph, but we're not looking at a graph, so we just remove them. And then finally, we print the image. We do cmap gray to ensure the image is gray and that's produced. And then we break it. If not, we produce an error. So actually, I'd like to start off with showing you what happens if we don't produce an error. So let's say I want an image, Purdue arc .jpg. And it says, oh, it doesn't look like I can support this file type. Perhaps a later version I can. So obviously it doesn't work. So let's see what happens when I take this and run Purdue arc.png. Now it does take a while. This is a lot of matrix algebra, as you can see, and a lot of loops. There's certainly more efficient ways to do this, but this is a very, very rudimentary way to do it in a way that shows understanding of what the project actually was. You can speed this code up, for instance, as I was considering running this code through something called Numba, which would run the code on your GPU. So if we look over here, this was the Purdue image, and it has been edge detected over. And if I open some files here, yes, so this would be the Purdue image. I'd actually like to go into my files here and go into documents so we can actually see what the Purdue arc looked like before. So this was the Purdue arc before. You can see the edges over here, and you can see the edges of the craters of the moon. And over here, we've detected the edges, including the craters of the moon. So the next one that we like to go through would be coins.png. This is another provided image. So actually, while that runs, because like I said, it does take a while to run, we're going to take a look at what coins.png looked like before. So this is what coins.png looked like before with all the color. We expect the edges to be here and here and here. And let's see what the result is. So over here, we have the coins.png, and we have the edges detected over here. So we can see there's some edges here because there's a crater here and then colors. It's a little bit of noise in the image, but that's because the image was, there's some things that cause peaks, for instance, over here. And then finally, we'd like to run sample.png. This will give us an edges of a Rubik's Cube. That's pleasant. If you can hear, my computer is currently really trying. Hopefully you can't hear it, but it is certainly trying. And this is a demanding task for a computer. And here we have pretty much perfectly produced edges. It looks really nice if you ask me. And there we go. So that's Team 13's project. Yet again, this is our edge detection project. And we have our group members, Jose Miguel Haro, Adrian Prasad, Emma Block, Hanu Gos. Thank you for watching this presentation.